So, today we are going to start our next topic, which is kinetics. Okay. So, in next 6 lectures we will cover the topic of kinetics, and in the first 3 lectures that we will have, we will be covering the topics of Cauchy stress tensor, equilibrium equations and principle of virtual work. Okay. So, following are some of the topics that we are going to cover, not necessarily in this lecture, but in the coming lectures. So, we will discuss conservation of mass, then the Reynolds transport theorem that we did towards the end of kinematics will now be specialized towards extensive quantities. Okay. And then we will discuss balance of linear momentum, followed by Cauchy stress principle, and finally, we look into the Cauchy stress tensor. Okay. We will also look into what is meant by objectivity and what is the effect of rigid body motions and what are its implications on stress objectivity. Okay. Finally, we will derive equilibrium equation and then we will do principle of virtual work. Okay. So, in the previous lectures we had derived kinematic fields. Okay. So, to characterize the deformation of the body. Okay. But these fields alone cannot predict the final configuration or the current configuration of the body under the action of external loading. Okay. So, just by knowing the kinematic fields, it is not possible that you be knowing the final configuration of the body. There is something more which is needed. Okay. So, to predict the final configuration, we require the generalization of the laws of mechanics, which are defined for the particles, okay, to the continuum systems or the continuum bodies. Okay. So, we already from our undergraduate and our first year engineering courses, we know the laws of mechanics applied to particles or system of particles. Now, we have to generalize these laws of mechanics to continuum bodies, okay, bodies which have infinite number of particles, okay, that is continuum particles. Okay. So, some of the laws of mechanics, okay, which we have to generalize consist of laws of conservation of mass, law of balance of linear momentum, law of balance of angular momentum, conservation of energy, and finally, the second law of thermodynamics. Okay. So, the last two, which is the conservation of energy and second law of thermodynamics, these two topics will not be dealt in this course, okay, because this is not a course on fully on continuum mechanics. So, we will just look into the first 3 laws, okay, how they can be generalized from system of particles say to continuum bodies. Okay. So, we in the present course we just study the first 3 and introduce the concept of stress and equilibrium for a deformable body undergoing finite motion. Okay. So, we will not deal with conservation of energy and second law of thermodynamics. Okay. So, in this present course our material will be hyperelastic material, okay, and that would be already satisfying the second law of thermodynamics. Okay. So, all the constitutive relations that we will derive will always satisfy the second law of thermodynamics. Okay. Now, coming to the topic of conservation of mass. Okay. Now, you consider that a body, okay, is in the current configuration, okay, as usual B0 is the current volume bounded by surface del B0 at time 0, and then after deformation at time t it is occupying a configuration B, okay, by and bounded by surface del B. Okay. So, from the law of conservation of mass, okay, we know that the mass of this body before the deformation, okay, let m be the mass and this bracket B0 means it is a mass of the body in the reference configuration. Okay. So, the mass of the body in the reference configuration will be same as the mass of the body in the current configuration or the final configuration, okay, or in the deformed configuration. Okay. So, that is what law of conservation of mass tells us, that mass will not be created or destroyed. Okay. Now, if that has to be true, now let us calculate a mass expression for this mass in the reference configuration as well as in the deformed configuration, and let us see what we come up with, what kind of equations we have to deal with. Okay. So, now if you consider a small, say if you consider a small infinitesimal mass dm. Okay. So, as the body deforms, this infinitesimal mass also deforms. Okay. Now, from law of conservation of mass, the mass of this differential element before the deformation should be same as the mass of the differential element in the deformed configuration, which means okay, the mass is nothing but density times the volume. Okay. Let dV be the volume in the deformed configuration and let dV0 be the volume in the reference configuration. So, let density in the reference configuration be rho 0 and the density in the deformed configuration be rho. Okay. So, the differential mass dm in the deformed configuration will be given by rho times volume dV, and in the reference configuration will be rho 0 dV 0. Okay. Remember, rho is a spatial quantity here, which means it depends on the spatial coordinates, and rho 0 is a material quantity. Okay. It depends on the material coordinates. Okay. So, now if I can, to get the total mass in the reference configuration, what I have to do? I have to integrate. Okay. So, I have to integrate this expression over here over the entire volume of the body, and this is what I get. So, I have to do this integral over the entire body of the quantity rho 0 dV 0. So, I have explicitly put here in bracket x comma t to show that the density in the reference configuration depends on the reference coordinate. Okay. Rho 0 is in the material description. Okay. Similarly, I can get the mass, total mass of the body in the deformed configuration. Okay. And this is obtained by taking integral over this quantity over the current volume. Okay. Integral rho dV. Okay. So, here you see rho is explicitly a function of spatial coordinates and time t. Okay. So, now if I use equation 1, equation 3, equation 4, which means I take equation 3 and 4 and I substitute this in equation 1, what do I get? Okay. I get the integral, okay, the volume integral of rho 0 dV 0 should be equal to the volume integral rho dV. Okay. Now, I also know from our discussion in the kinematics that the relation between the volume element in the spatial configuration and the volume element in the reference configuration is given by dV equal to j dV 0. Okay. So, what I can do now is I can substitute this over here, okay, and then I can write and I can bring the integrals on the left hand side. So, I can write the integral, volume integral over the reference configuration, okay, rho 0 minus rho into j dV 0 equal to 0, okay, which means the now because this is applicable for any body, which means this integrand here, okay, that you see here, this is the integrand, this has to be equal to 0. So, what do you get? You get rho 0 equal to j times rho, okay, which means the current density times the Jacobian equal to reference density. Okay. So, remember this we also derived during kinematics. Okay. So, this equation 8 is called the material form of the conservation of mass. Okay. So, that is a material form, which means there has to be, I mean there can be something called spatial form. Okay. So, this is a material form. Now, if I say this is material form, definitely there is something called spatial form. Let us see. Now, we try to get the spatial form of the conservation of mass. Okay. For this, what we have to do is, we have to take the material time derivative of equation 4. So, equation 4 was m, okay, m b equal to rho dV. Okay. Now, if I take the material time derivative on both the side d by dt of this, okay, so it will be d by dt of this quantity over here, that is what we have written. Okay. Now, if you remember the Reynolds transport theorem that we discussed towards the end of kinematics, okay, and which is reproduced here, Reynolds transport theorem for an integral quantity, okay, of a spatial quantity. Okay. So, if I had, remember, if I have to take the material time derivative of an integral quantity I, which is integral of a spatial quantity g, okay, over the current configuration, then Reynolds transport theorem told me that the material time derivative of the integral will be nothing but g dot plus g divergence of B. Okay. Now, in our case here, if we see our g here, okay, so if I compare equation 10 with equation 9, okay, I can see g x comma t is nothing but rho x comma t. Okay. So, using this Reynolds transport theorem, I can evaluate the right hand side of equation 9, and because the mass does not change with time, the material time derivative of the mass is nothing but is equal to 0. Okay. So, now if I use the Reynolds transport theorem, okay, what do I get? d m by dt, or I can write m dot is equal to integral over the current configuration rho dot plus rho divergence of V. So, this is rho is your g. So, all we have done is replaced g by rho in equation number 10. Okay. Now, what happens? This quantity, okay, is equal to 0, which means the integrand must be equal to 0. Okay. And the integrand has to be equal to 0, which means this quantity over here. Okay. So, what I have done between these two is I have just dropped the explicit dependence on the spatial coordinates and time t. Okay. So, this quantity in the bracket, okay, which is the integrand, has to be equal to 0, okay, for equation 12 to hold. Okay. And this equation number 13 is called the spatial form of the conservation of mass. Okay. So, the material form was rho 0 equal to j rho. Okay. That was the material form of the conservation of mass, material form of conservation of mass. Okay. And the spatial form of conservation of mass is given by rho dot plus rho divergence of V. Okay. Now, again I can simplify equation 13 further. Okay. So, to do this, what I can do is I recall the concept of material time derivative of a spatial quantity. Okay. Remember, the material time derivative of a spatial quantity g, okay, which is written as g dot, okay, is nothing but del g by del t, okay, which means I keep x fixed here, del g by del t plus the gradient of quantity g times the velocity. Okay. So, del g by del t plus the gradient of the quantity g plus the velocity. Okay. Now, if you see our expression number 13, we have the material time derivative of density sitting over here. Okay. So, I can express, and that density rho, okay. So, this density rho here is nothing but a spatial quantity. So, if this is a spatial quantity, then using the concept of material time derivative, I can write g dot, okay. So, this is the equation. So, okay. So, I can write our g is rho. So, I can write rho dot as del rho by del t plus gradient of rho times velocity plus rho times divergence of v, okay, that is here, okay, equal to 0. Now, I can now concentrate on these two expressions. Okay. So, this is nothing but, if you do, you can show that this is nothing but divergence of rho v. How? I can show divergence of rho v is, in indicial notation, I can write rho, this is v I bracket comma I, and this is nothing but rho comma I v I plus rho v I comma I. Okay. So, rho I is nothing but gradient of rho times velocity plus rho times divergence of v. Therefore, divergence of rho v is nothing but gradient of rho times velocity plus rho into divergence of velocity. Okay. So, that is what we had here. Therefore, this is what we get. Okay. So, combining the last two terms, we can get del rho by del t plus divergence of rho v equal to 0. Okay. And this equation number 15 is also called the continuity equation. It is used a lot in fluid mechanics. Okay. Not so much in solid mechanics, but in fluid mechanics. Okay. So, now the next topic we have specialization of Reynolds transport theorem for extensive quantities. Okay. Now, what are extensive quantities? Extensive quantity is a quantity which is proportional to mass. Okay. So, if G is an extensive quantity, so it will be proportional to density. Okay. It will be equal to density times phi, okay, where phi is a density field, which means G is per unit mass. Now, if you have certain quantity like this, then your Reynolds transport theorem, which is again reproduced here. Okay. Remember, Reynolds transport theorem allowed you to compute the material time derivative of integral of a spatial quantity over the current configuration. Okay. So, and it was given by following expression. Now, let us see if we have a special case where G is equal to rho times phi. Okay. Rho is density and phi is your density field. Then what I can do is I can substitute G equal to rho phi in this expression. Okay. If I do this, I will get rho phi dot. Okay. So, this is nothing but the material time derivative of rho phi plus rho phi times divergence of v. Okay. So, this is G, okay. So, which is nothing but rho phi. Okay. So, I have just substituted G equal to rho phi. Now, I can expand this term. Okay. So, it is a time derivative of product of two quantities. So, I can expand that and that would become rho phi dot plus rho dot phi, plus there will be the second term over here, which is rho phi plus divergence of V. So, I can take rho dot phi plus rho phi divergence of V inside the bracket, and I can take out. So, because phi is common in both the expression, I can take out phi out from the right hand side, okay, and then I get rho dot plus rho divergence of V. Okay. So, I get rho phi dot plus phi times rho dot rho divergence of V integrated over the current configuration. Okay. Now, if you remember the continuity equation, okay, or if you basically remembered the spatial form of the conservation of mass. So, this is your same expression, the spatial form of the conservation of mass. Therefore, this is equal to 0, okay, because we have said rho dot plus rho divergence of V is equal to 0. If that is equal to 0, we get the material time derivative of an extensive quantity, okay, that is extensive quantity integrated over the current configuration as integration of rho times the material time derivative of that extensive quantity integrated over the spatial configuration. Okay. So, d by dt of B rho phi dV is nothing but integral over B rho phi dot dV. Okay. So, equation 16 is very helpful, okay, and we will see its utility in the coming slides. Okay. So, this is the specialization of the generalized Reynolds transport theorem for extensive quantity. Okay. Now, we come to discussion on balance of linear momentum. Okay. Now, before we begin the balance of linear momentum for continuous body, let us start with balance of linear momentum for a single particle. Okay. So, we know that from the principle of conservation or the balance of linear momentum, and the linear momentum is denoted by bold L. Okay. For a particle of mass m and occupy position r under the action of external forces, okay, given by F subscript external. Okay. So, let me write F subscript external is given by the material time derivative of the quantity L is equal to the net external force acting on the body. Okay. Material, because I am concentrating my attention on a particular particle, I am not concentrating my attention on a particular position. That is why I have to take a material time derivative. That is why you have d by dt of L. So, the rate of change of linear momentum is nothing but the net external force acting on the particle. Okay. Now, if the particle mass was m and its position was r, then its linear momentum is given by m r dot, okay, where r dot denotes the current velocity, okay, and F external is equal to small f. Okay. So, F is the external force acting on the particle. Therefore, if we substitute these two expression in equation number 17, what we get d by dt, that is the material time derivative of the linear momentum m r dot is equal to external force F. Okay. And because the mass is constant, the mass does not change, okay, because this would be equal to m dot r dot plus m r double dot equal to F. But now, since mass does not change, the first quantity is equal to 0, and then what we get for a constant mass, we get mass times acceleration equal to net external force acting on the particle. So, this is nothing but the Newton's second law for a rigid particle, okay, of mass m currently located at position r under the action of forces, net external forces F. Okay. Now, consider a system of n particles, and let m I and r I be the mass and position vector of the ith particle, okay, and I goes from 1 to n. Okay. So, then the total linear momentum of the entire system of particles will be nothing but summation over the linear momentum for ith particle. Okay. So, this is nothing but m 1 r 1 dot plus m 2 r 2 dot, okay, like all the way up to m n r n dot. Okay. So, this is the total linear momentum for the system of particles. Okay. Also, let the net external force be given by summation over F I, where F I is the net force acting on the ith particle. Okay. So, the net force on the ith particle F I, if you add for all the particles, you get the net external force. Okay. And now, we know that from Newton's second law, the rate of change of linear momentum is nothing but the net external force acting on the particle. Therefore, when we substitute equation 18 and this equation on the right hand side, what we get? We get m I r I double dot equal to F I and summation over I equal to 1 to n. Okay. So, this is the equation for Newton's second law for a system of particles. Okay. Now, what we want to do is let n go to infinity. Okay. When n goes to infinity, we have infinite number of particles, and that where we will be able to approximate our continuum. Okay. So, our continuum is composed of continuum particles, infinite number of continuum particles. So, now our job is to now let n tend to infinity. Okay. That is where we are going to get our continuum particles. So, we want to generalize the Newton's second law for a system of infinite particle, that is a continuum. Okay. So, in that case, now let us consider our body, okay, at time t. It is occupying the configuration B, it is bounded by del B. Okay. Now, if you consider a small infinitesimal volume, okay. So, the mass of this is dm, volume is dv, and the density is rho. Okay. Then the linear momentum, okay. So, this is the zoomed view of that particle. So, the linear momentum of the particle is x dot into dm. Okay. So, x dot is the, say x dot may be, x is the current position. Okay. With respect to the coordinate system, that is current position. So, the velocity is x dot and the momentum is mass times velocity, mass is dm, velocity is x dot. So, the linear momentum of this infinitesimal mass is m x dot dm. Okay. So, integrating over the whole volume, okay, we can get the linear momentum of the entire continuum body. Okay. So, the total linear momentum of the body, okay, in the current configuration B is nothing but integral over the entire volume of dl. Okay. Now, if I substitute dl as dm x dot from equation number 20, this is what I get. Okay. And then because dm was rho dv, I will get equation number 21 for the expression for total linear momentum of the body, continuum body, which is nothing but integral over the current volume x dot rho dv. Okay. Now, the total linear momentum, okay, okay, and I can take the material time derivative of the total linear momentum of the body, and that should be equal to the external force acting on the body. Okay. So, here F external is the total external force acting on the body, and the total external forces can be categorized into two types. Okay. One are called the body forces. Okay. So, the body forces are forces that act at a distance. Okay. So, the cause of these forces are present at a certain distance from our continuum body. Okay. They are not nearby the body, they are at a certain distance, and because of certain effect the body experience certain forces. The whole body experience certain forces. So, what happens? The body forces act over the entire volume of the body. Okay. And some of the examples of body forces are gravity force, electric field, electromagnetic field, centrifugal force, Coriolis effects, etc. Okay. So, these are some of the examples of body forces. Remember, body forces act over the entire volume of the body. Okay. Now, the surface forces. Okay. The second type of forces are the surface forces. Now, surface forces are forces which act at a short range across the surface of the body. Okay. And they result from the interaction of the body with its surrounding. Okay. So, surface forces act over the surface of the body as the name suggests, and one of the example of the surface forces are the contact forces. When you make one body come in contact with the another body, then you have surface forces. Okay. Now, our next job is to obtain an expression for the net external force of the body when both the body forces and the external surface forces act over the physical surfaces of the body. Okay. Physical surface and volume of the body. So, now let us see. So, let us start with the getting the expression for the body forces. Okay. So, our volume, okay, small infinitesimal volume, let it be acted over by body force density field B, okay, which may be dependent on the configuration, current position of the point. Okay. And this body force density field is per unit mass. Okay. Then the total body force, okay. So, the total body force will be integral of the body force density field B times the infinitesimal mass. Okay. So, if B is body force per unit mass, then the body force for this small infinitesimal element would be B times dm. So, the total body force will be nothing but integral over the entire volume, okay. Sorry, integral over the entire volume, and dm is nothing but rho dV. So, equation 23 gives you the expression for the body forces. Okay. For example, let us take the case of gravity force, and let us see if you have a gravity force acting in the negative E2 direction. Okay. Say x1 direction is your horizontal plane and x2 is the vertical plane. So, the gravity forces act in the negative x2 direction or negative E2 direction. Okay. Then the body force are given by minus g times E2, where g is nothing but the acceleration due to gravity. Okay. So, the body force field is given by minus g E2. Therefore, the total gravitational body force, okay, in case your body force is composed of gravity, is given by integral of minus g E2 over the entire body. Okay. Now, g is a constant, okay, 9.81 meter per second square. So, it can be taken outside. E2 is a constant, in our case in this course it is a constant, it can be taken out. Okay. So, therefore, we have left is integral of mass, and this is nothing but the mass of the body in the current configuration. Okay. So, this is minus m times g E2 is nothing but your total body forces, net body force acting on the body. Okay. Now, let us see expression for the surface forces. They are also called the contact forces, and they are defined in terms of the surface density field of force per unit area. Okay. Remember, they are defined in terms of surface density field of force per unit area, which is also called as traction field. Okay. So, the traction is force per unit area. Okay. Now, consider you have this small area on the surface of the body, the area is dA and the normal to this area is n, okay, and the traction is given by T, bold T. So, the total, because traction is force per unit area, that force acting on this infinitesimal area is nothing but d surf, okay, d subscript surf. Surf is there to show that this is force on the surface. That will be nothing but force per unit area times the area dA. Okay. So, therefore, the resultant external interaction force across this surface is given by delta F surf. So, the limit of this force per unit area dA is defined as the external traction or the stress vector. Okay. So, it is usually denoted by symbol T bar. Okay. So, bar over the traction suggests that it is a external specified traction, and this is nothing but limit delta A tends to 0, the ratio of delta F divided by delta A, and in the limit delta A tends to 0 becomes dF by dA, that is force per unit area. Okay. Now, a fundamental assumption in continuum mechanics is that this limit, okay, that is in the previous slide we were taking limit delta A tends to 0 delta F surf by delta A. So, T bar was defined as this. So, fundamental assumption in continuum mechanics is that this limit exists and it is finite and it is independent of how the surface area is brought to 0. So, what you are doing is you are bringing the surface area to 0, which means you are concentrating more and more at a point, you are approaching towards a point. So, even if you approach towards a point, the limit of this quantity exists, and that is called the externally specified traction. Okay. Now, the total force on the physical surface of the body can then be obtained by integrating the differential force over the entire physical surface of the body. Okay. So, this is the force on the area infinitesimal area dA. Okay. So, the total force over the physical surface of the body will be nothing but integration of this quantity over the surface of the body, which is del B. Okay. And now, because dF surf is nothing but T bar dA, I get the total surface force as T bar dA integrated over the current surface of the body. Okay. Hence, the total external force will be nothing but the sum of the body forces and the surface forces. So, the sum of total body force plus the sum of total surface forces. So, F external will be sum of the body forces, total body forces plus the sum of external tractions. So, this is body forces and this is surface tractions. So, total force equal to body force plus surface traction. Okay. Now, we have obtained the expression for the net external force, total net external force acting over the continuum body, okay, which is del F external, that is F external. So, now if we substitute the expression for the external forces in the following expression. Then we have the material time derivative of the linear momentum, okay, total linear momentum is equal to net external force, that is which is equal to the sum of the total body forces and the surface forces. Okay. Now comes the application of Reynolds transport theorem for extensive quantity. If you see here, okay, our phi here is x dot, which is function of x and t. Okay. X dot is nothing but velocity. Okay. So, we have a velocity field which is multiplied by density rho. So, from our Reynolds transport theorem for extensive quantity, okay, we can just simply take rho times phi dot, and because our x dot was equal to phi, so phi dot becomes x double dot. Okay. So, we get the integral or the current volume rho x double dot dV is equal to the net external force, that is the sum of total body forces and the total surface forces. Okay. Now, a special mention I should have is that sometimes the body forces B is given in terms of per unit volume instead of being given in terms of per unit mass. If the body forces are given in terms of per unit, body force field is given in terms of per unit volume, then equation number 28 boils down to this expression. So, the only difference is here you do not have rho, density is absent, because B here is force per unit volume. Therefore, you have to just multiply by volume to get force, unit of force. Here B was per unit mass. So, you have to multiply by mass to get the expression for force. Okay. Now, we come to the concept of Cauchy stress principle. Okay. Now, to obtain the local expression for the balance of linear momentum. Now, what we have here, this is the global expression for balance of linear momentum. Okay. Now, we want to get the local expression. Why local? Because now we have the case of a deformable body and we wish to determine the local response, the response at every location. We wish to develop an equation which can give us the deformation at each and every point inside the body. Therefore, we should have some local expression for the balance of linear momentum. Okay. For that, it is important that we obtain an expression like this here, the global expression for balance of linear momentum for an arbitrary internal sub body E of body P. Okay. Now, if you have a body B, okay, so we already have this expression for this body B. Now, if I take a sub body, okay, E of this body B, okay, then I should be able to have the similar expression, okay, for this sub body E. Okay. So, now to get this expression for this sub body, that is not a problem for these two volume integral terms, okay, because you can write these expression because they are volume terms. You can just take the volume integral over the volume of the sub body to get the local expression for the left hand side term and the first term on the right hand side. The problem occurs for the second term on the right hand side, because that term is the integration of the applied tractions over the physical external surface of the body. And because this body sub body E is internal, so we do not know the tractions on this body. We know the externally applied tractions, okay, T bar, but we do not know what is the distribution of traction on the surface of this subbody E. Okay. Now, this problem was addressed by Cauchy in the year 1822, where when he gave his famous stress principle, which lies at the heart of the field of continuum mechanics. Okay. What Cauchy gave, okay, that is his Cauchy stress principle addressing of this problem, okay, where we did not know how the tractions acted, okay, on the internal surface of the bodies. Okay. So, Cauchy realized that there was no inherent difference between the external forces acting on the actual surfaces of the body and the internal forces acting across inside surfaces of the body. Okay. So, what he realized that the way the external tractions act on the external surface of the body, the internal tractions will act in a similar way on the internal surfaces of the body. Okay. So, once Cauchy realized that, okay, he theorized that both of them can be described in terms of tractions distribution, okay, and this made sense because in the end external tractions characterize the interaction of a body with its surrounding. Okay. So, the external tractions characterize how the body is interacting with the surrounding, okay, like the other bodies, and the internal tractions characterize the interaction between the two parts of the body across an internal interface. Okay. So, once Cauchy realized that, he gave his famous Cauchy stress principle, which is stated here in concise manner, and it states that the interactions of the material across an internal surface in a body can be described as a distribution of tractions in the same way that the effect of external tractions on the physical surfaces of the body are described. Okay. So, this is rather very simple statement, okay, and currently it may seem very trivial, but imagine 200 years back this was a very revolutionary idea, and this paved the way for the continuum theory of solids and fluids. Okay. Now, what we will do is we will come up with the mathematical expression, okay, of Cauchy's stress principle. So, what does this mathematically mean? Okay.